students. So far we have completed important and large part of this chemical bonding, Vsepr model, and hybridization and Lewis structures. See, in Lewis structure, there is no, idea about bond angle, bond length, geometry, shape. But in Vsepr model and in hybridization, we have to take care of this geometry, shape, orientation of different bond pairs, lone pairs. So this is the difference basically. Means when you are writing the Lewis structure of any molecule, so you don't bother about the orientation of atoms or group of atoms in space with respect to each other. But when you are treating any molecule as per hybridization or Vsepr model, so you have to take care of the orientation of different groups, atoms, lone pairs, what is the electronic geometry of that molecule, and what is the shape of that molecule. So all these things you should taken care of. So now in this lecture I am going to discuss some of examples of molecules, and after that I will shift to the new topic. So let's do some examples based on this valence bond theory, which includes hybridization and other Lewis structures. So I am taking first example, that is BRF5. BRF5, bromine pentafluoride. Bromine pentafluoride. Central atom is bromine here. So if you want to calculate the hybridization or number of hybrid orbitals, so which type of compound is this? Basically this is a interhalogen compound. This is the compound of halogen with halogen, right? So this compound is known as interhalogen compounds. Interhalogen compounds. Central atom is bromine. So C, bromine. What is the electronic configuration of valence shell electronic configuration of this bromine? Valence shell electronic configuration of bromine. What is the atomic number of bromine? 35. 35. So argon, and 3D10, 4S2, and 3D5, right? So this is the valence shell here. Valence shell electronic configuration is this for bromine, right? So number of hybrid orbitals, if we calculate number of hybrid orbitals is equal to half of the valence shell electron. So valence shell electron 5 and 2, 7, plus fluorine is monovalent. So how many fluorine are adding here? 5. So this is equal to 6. So 6 hybrid orbitals should be there. 6 hybrid orbitals means 6 electron pairs should be there. right? So the number of electron pairs in this molecule is equal to 6, means total 6 hybrid orbitals are there. So total, if you want to summarize all these things, in this molecule, number of electrons contributed by bromine, so number of electrons from both bromine, so you have to do like this. You have to do the work out with molecules like this. Do each and every aspect of the molecule. Don't hurry in doing so many molecules, this type of workout. Do few molecules, 5 to 10 molecules, but do each and everything. What is the electronic configuration of central atom? How many electrons it is submitted? Because any question examiner can be asked. Okay, suppose that you are expert of finding hybridization. Okay, it's okay. And examiner has asked, okay, tell me which d orbital is involved in the hybridization of BRF5. And if you have not worked out properly, you cannot explain. You cannot give the answer. That 3D is involved or 4D is involved or 4S is involved. You cannot answer. So it is better to do complete postmortem of sum of molecules, at least from each hybridization, one molecule from each hybridization. So number of electrons from bromine, number of electrons from bromine is equal to 7, right? Number of electrons from 5 fluorine atoms, number of electrons from 5 fluorine atoms is equal to 5, right? 5. Now, similarly, total number of electron around the bromine, any question can be asked. Total number of electrons around the bromine is equal to 7 plus 5, 12. So is it obeying octet rule? The answer is no. It is superoctet? Yes, right? So this is 12. Number of bond pairs. Bond pairs is equal to 5. Number of 5 fluorine atoms are here for bonding, available for bonding. Number of lone pairs on bromine is equal to 1. And total number of lone pairs is equal to, each fluorine had 3 lone pairs, so 5 fluorine are there, so 5 3s are 15 and 1 this, total 16 lone pair of electrons are there in this molecule. Number of sigma bonds is equal to 5. Number of pi bonds is equal to 0, right? And what is the hybridization? So as per the 6 electron pair or 6 hybrid orbitals, now you can write the hybridization, that is sp3d2. And what orbitals are involved here? So 4s 4p, what I have written here, not 3d5, this is 4p5, right? 4p5. So what hybrid orbitals are, what atomic orbitals are involved here? So the atomic orbitals involved in this molecule, atomic orbitals of bromine are involved here. See, 4s, 4p and 4d. 4s, 4p and 4dx2 minus y2 and 4dz2. You know, all 5 orbitals are degenerate orbitals. 5d orbitals all are degenerate. So any one two, as per the symmetry, as per the requirement, these two are involved here, right? Now see, what is the electronic configuration of bromine in this molecule? What is the electronic configuration? Electronic configuration of bromine in this molecule is equal to 4s1, 4px1 or 4py1, 4pz1, 4dx2 minus y21, 4dz2 1. So here one lone pair is there. So in p orbital, anywhere you can take 2 electrons as a lone pair. So this is the complete electronic configuration of bromine, valence shell electronic configuration in this molecule. How many unpaired electrons are involved in this molecule? See, 1, 2, 3, 4, 5. So the number of unpaired electrons from bromine, although after the formation of molecule there is no unpaired electron, but before hybridization, before formation of molecule or before overlapping with fluorine, bromine has 5 unpaired electrons. So before overlapping with fluorine atom, the number of unpaired electrons in bromine atom is equal to 3, 4, 1, 2, 3, 4, 5. Right? So what is the electron geometry? Means electron pair. So if you see 6 electron pairs are there, so 6 electron pair. So you can say the geometry or electron geometry, you can say electron geometry is octahedra. And what is the shape of this molecule? So without if you consider without this lone pair, so the shape is a square pyramidal. Right? Now see, your bromine is here, and electronic geometry is here octahedra. So you know, in octahedra there is no axial, no equatorial, all bonds are equivalent. So one lone pair is there. So anywhere you want, anywhere you can put that lone pair. No restriction, right? Suppose that I have put it here. So fluorine is here, fluorine, this will form the base of the square, and this is the pyramidal shape. So this is a square pyramid. What should be the bond angle? You know, ideal bond angle is 90 degree here, but you know, if there is a lone pair, so this will push these fluorine atoms upward like this, like this, like this, like this. So due to this lone pair bond pair repulsion, there is no bond angle is 90 degree here. I think there is none of the bond angle is equivalent to 90 degree due to this distortion, or due to the presence of this lone pair, right? So number of 90 degree bond angles, answer is 0. So this is you can say this is somehow distorted octahedra, you can say, right? This is not the perfect square pyramidal structure, right? Because if it is perfect square pyramidal, then there is no distortion. So it is not a perfect square pyramidal structure. It is somehow distorted structure. So the bond angles are not equal to 90 degree. So bond angle is not equal to 90 degree, but not much deviated. It is close to 90 degree, right? See, if it is ideal structure, then this bond angle is 90 degree, this bond angle is 90 degree, all these bond angles are 90 degree, but here, due to the presence of this lone pair of electron, the bond angle is not equal to the 90 degree. So see, this is the complete explanation of the structure of a molecule. So all of you should try in this manner to deal with molecular structures, right? So this is BRF5 molecule. Now see another case, another example I am taking here, XeF6. XeF6. So if you see the FeX6, so what is the electronic configuration of genome? So if you see here, core is of krypton, and valence shell electronic configuration is 5s2 and 5p6. It is a noble gas, so obviously P will completely filled, and now it is core. So this is core, and this is what 5s2, 5p6. So if you see this 2 electron here, 5s2 and 5p. Right, and 5d0. So in hybridization, there is a change in the state of this electronic configuration, because until or unless there is no change in the state of electronic configuration, this formation of this molecule you cannot explain. So in the molecule, this is in free state. This is the electronic configuration in free state. And now in the molecule, see, there are 6 fluorine atoms to be bond here, through overlapping. So minimum you have 6 unpaired electrons. Minimum 6 unpaired electrons should be there. So see, this is core, and this 5s2, 5p6, X, 5p Y, 5p Z, and 5d x2 minus y2, 5d z2, and 5d xy. So minimum one electrons should be there, like this. So if you promote this one electron here, this one electron here, and this one electron here. So this is the state of electronic configuration of this xenon atom in this molecule, right? So in the bonding of this molecule, 5s, 5p, and 5d orbitals are involved. Okay, right? Good. Now, number of electrons contributed by this xenon in this molecule, 6 and 2, 8. So the number of electrons. Now I am not going to write each and everything what I have written for the previous molecule. All of you should note down yourself. So number of hybrid orbitals we can take directly. So this is equal to 1 by 2, 8 by this xenon, 8 electrons total you have to count here, plus 6 here. So you will get 7 hybrid orbitals. Means 7 electron pairs basically. So 7 hybrid orbitals you will get where? In sp3d3. So the hybridization is here sp3d3, and there are 7 hybrid orbitals are there. But you know, this molecule has some problem. This experimental observation shows that as per this hybridization, this should be p pentagonal. Geometry should be pentagonal bipyramidal, PBP. This should be like this. Should be as per hybridization. As per hybridization. But in actual case, in octahedra you have total 8 trigonal faces. So this lone pair, instead of taking the orientation of this PBP, perfect PBP, this lone pair is oriented at the one of the trigonal face of the octahedra. So this is the reason why its geometry is capped octahedra. Capped octahedra means the rest of the fluorine, all 5 fluorine, 6 fluorine, they occupy the 6 octahedral positions, and when this lone pair that will occupy the one of the trigonal face at the center of the trigonal face. So if you see here, xenon, see, this is okay. So this is one of the structure of octahedral structure. So fluorine are like this, and you know, this is one of the trigonal face of this octahedra, right? So this lone pair is somehow in between like this here. It is not oriented as directly in what pentagonal bipyramidal orientation. So geometry should be reported like capped octahedra, and you cannot say that all the bond angles are now perfect 90-degree. This is not possible here. So the shape of this molecule is reported like shape is distorted octahedra, right? So the shape of this molecule is distorted octahedra, and geometry is capped octahedra. And as per the hybridization, sp3d3 suggested that this should be pentagonal bipyramidal, but it's X-ray diffraction technique what gives the structure of this molecule that will not match the credentials of this pentagonal bipyramidal. That credentials are more close to the octahedra. So we should say like that that this is a distorted octahedra, not the pentagonal bipyramidal, right? So this is I mean an exceptional molecule, and this is true for every I mean molecule of this type of structure AX6, and if A is sp3d3, so definitely you have 6 bond pair and 1 lone pair. So if there is in any molecule this situation arises, so you have to report geometry capped octahedra, capped octahedra, and the shape is distorted octahedra. Why this happens? This is something related to the repulsions between fluorine and their lone pairs in the space. As all of you are knowing that in PBP, pentagonal bipyramidal, there are I mean 72-degree bond angle and 90-degree bond angle, but here all the bond angles are close to 90-degree. So this will give way to fluorine atoms, so minimize the repulsion basically. So this is all due to the repulsion in space between these fluorine atoms. So they will always try to make present at maximum distance from each other, so their energy should be minimum, right? So see, mere finding of hybridization is not everything for the study of any molecule. Study of any molecule includes each and every aspect, that what electronic repulsions it has, and what okay, this hybridization may help you to just make some opinion about the molecule, that okay, molecule should be like this, but the actual fact we will get from the experiment only. So whenever now it is clear that if any molecule of this general formula AX6 having sp3d3 hybridization with 6 bond pair and 1 lone pair, so this statement is always true, right? So these two molecules I have discussed. Now in the same manner you can discuss. You should draw the structures. I will give you the homework at the end of this lecture, right? So now see, sometimes it is given that what is the hybridization in phosphorus, in phosphorus, in PCl5 solid. So see, in solid state, many molecules changes their state as per the requirement and energy of the system. They are changing. So if you do not know the what exactly this PCl5 exists in which form in solid state, you cannot answer such type of questions. So you know this PCl5 basically in solid state this exists as a PCl4 plus PCl6 minus. So if such type of question is asked, so you have to answer these two. Means hybridization is here and here. Don't try to give the answer in the hybridization here. So it's 2 moles. They will, rearrange themselves. I mean, one chlorine, one has lost one chlorine. So to minimize the repulsion, basically to minimize the energy of the system. So until or unless you don't know that which compound in solid phase exists in which form, you cannot answer such type of questions. So now you are able to answer this question that if you know that this PCl5 exists as a PCl4 plus and PCl6 minus. So here hybridization, what should be the hybridization here? 5, 4, 9, 8. So this is sp3. And here 5, 6, 11 and 12. So this is sp3d2, right? So this is tetrahedra and this is octahedra, perfect octahedra. There is no distortion because there is no lone pair of electrons in any one of these, right? So your answer is sp3 and sp3d2. So like this PCl5, now you will draw the structure and everything. I will discuss one, of this case. Okay, let's discuss this PCl5. So, sorry, PCl6 minus, because there is some point here that I must tell you, all of you, that in PCl6 minus, what is the valence shell electronic configuration for phosphorus? So, you have 3s2, 3p3 and 3d0. So sp3d2, so 2 unpaired electrons should be there. So it is its electronic configuration is like this. 1 electron is here and 3 electron here and 2 more electron here. 3 is already there, so only 1 electron will come here. But that is the point I want to explain here. 1, 2, 3, 4. 1, 2, 3, 4, 5. See. So in this case, what orbitals are involved in hybridization? This is 3s, this is 3px, 3py, 3pz, and this is 3dx2 minus y2. But here, sp3d2 means one of the d orbitals should, also involve here 3dz2 without electron. So in the beginning of hybridization, as I have already told you, that in hybridization, any kind of orbital like valence orbital, like empty orbital, like fulfilled orbital, all can mix. So here all these 5 orbitals, 6 orbitals, 3, see these orbitals mix. So these orbitals mix and produces 6 sp3d2 hybrid. So there is a difference in the bonding. See, 5 chlorine will bond with a covalent bond, overlapping type of bonding, covalent, normal covalent bond, but 1 chlorine should bond through the coordinate, means both the electron pair is provided by chlorine. So this is the difference. All six bonds are not equivalent, means all are not formed by the same type of overlapping. One bond is here that is formed by the coordinate bond, right? So if we try to represent here, see, this is octahedra. So one bond is different from other bonds, that this Cl minus is providing both the electrons, although there is no difference once they are formed, but see the difference in its explanation. See, this is the structure of this molecule. So you have 5 normal covalent bonds. These are normal covalent bonds, and this is something different. It has, in this case, in this covalent bond, both the electron pairs are provided by chlorine. It is not the mutual sharing. It is sharing, but it is not the mutual sharing, right? So how this, we can explain. So very simple, that these two electrons are present in one of the atomic orbital of chlorine, and that atomic orbital will fully overlap with the this empty hybrid orbital, and this give rise to the covalent bond. So there is overlapping. Don't see that here there is no overlapping. There is overlapping, but this overlapping is something different. This is, suppose that P so these are, all 6 sp3d hybrid orbitals, each have have one electron, and this is empty, right? This is empty. So chlorine will overlap, each chlorine will overlap here with one electron. Each chlorine is overlapped with one electron. So 5 chlorine, they overlap with one electron, but one chlorine atom, overlap with 2 electrons with this, right? So this is the difference basically, right? See, this is one of the explanation. And other explanation, that you should give this negative charge to the phosphorus. So each chlorine will, overlap equivalently, right? So these are the different explanations. Although there is no difference once the this overlapping takes place, right? After overlapping, after the formation of molecule. So this is PCl6 molecule, because sometimes it may be asked, and it is justified, no problem, because chlorine is more electronegative. So obviously, if there is a chance of to accept the electron, obviously chlorine will accept the electron, not phosphorus. So this is very much justified, right? So now, if you do not have idea that which compound are in solid phase exist how, then you cannot answer the question. So I am giving you some list of such compounds which exist in solid form, in which form. So see, suppose that PBr5 is there. So this PBr5 solid, this exists as a PBr4 plus, and this ionic species, one ionic species PBr, Br minus, right? So here you have to report the hybridization here, not here. So what is the hybridization? sp3. So if you want to argue, you can argue that why not here like PCl6, PBr6. So as you know, the size of this Br is large. So when you try to arrange this 6 bromine atoms around the phosphorus, the system is unstable. So you won't get this PBr6 minus. Similarly, in PF5 also you won't get PF4 plus and PFCl6 minus. That is also not possible, and PI. So only in series of this PCl4, PCl5, PBr5, only you will have this PCl5, that PCl4 plus and PCl6 minus, and PBr5 plus, that is PBr4 plus, and this. So you have to report the hybridization here. Similarly, if you have this IF5, this is, I think it is liquid at room temperature, not solid. So this will exist as a IF4 plus. So whenever molecule have chance to reduce the steric hindrance, steric repulsion, so it will do, right? So ICl4 plus, IF4 plus IF6 minus. So basically 2 moles of this, they will interact with this. So you have to report the hybridization here and here. So what is the hybridization here? 7 for what? 11 minus 1, so this is sp3d, and here 7 and 6, 13, 14, so this is sp3d3, 6 bond pair, 1 lone pair, so this geometry is capped octahedra and shape is distorted octahedra, right? So this is IF5. Now see N2O5. N2O5 solid, in solid form this will exist as a NO2 plus and NO3 minus, right? So 514, so here you will have SP hybridization, and 6, so this is sp2. Now you have to calculate all these things and show the formation of all these molecules. This is homework for you people. You should, I am writing here hybridization, and you should draw the complete structure, do everything, electronic configuration, geometry, shape, everything you should write in your notebook, right? Similarly, N2O4 solid, if you take N2O4 solid, so you will get what? NO plus and NO3 minus. So here again SP and 5 and 6, this is SP2, right? Similarly, if you have XEF6 solid, it is given, so you will get XEF5 plus and F minus, right? So you have to report here. So it is 8, 8 and 5, 13, 13 plus 1, so 12, so this is sp3 d2, right? sp3 d2. Similarly, if you have Cl2O6 solid, so after dissociation in solid state, this will give ClO2 plus and ClO4 minus. So 7, 7, 6, so this is sp2, and 7, 1, 8, so this is sp3, right? Similarly, if you have I2Cl6, so I2Cl6, this solid exists as a ICl4 plus and ICl2 plus ICl2 plus ICl4 minus, right? So 7 and 2 9 and 10, so this is sp3, 7 4 11 12, this is sp3d2, right? Similarly, if you have I2 solid, I2 solid, so I2 solid basically exists as a I3 plus and I3 minus 3I2. So here SP 7 to 9 SP3, here this is SP3 and 7 to 9 and 110 SP3D, right? So these are the certain popular molecules which exist in different state in solid state, different form in solid state. So you have to report the hybridization like this if it is asked to you, right? So this is these are the certain examples of hybridization. Okay. Now see one important note here. Uh, I'm trying to explain something relation between hybridization and bond angle, and this is the end of this discussion, basically hybridization. After that, I will take up the next topic. So the relation between hybridization and bond angle for simple sp hybridization or sp hybrid orbitals, it is very simple. Means for simpler molecules, you can find out the relation between hybridization and bond angle. So see the relation between hybridization and bond angle is simple for sp hybrids. For sp hybrids, sp hybrids means for sp2, sp3 and sp hybrids. For two or more for two or more equivalent hybrid orbitals, equivalent hybrid orbitals, hybrid orbitals, the percent s character, the percent s character s character s and percent p character, percent p character is given by cos theta is equal to s by s minus 1 is equal to p minus 1 by p. So this is a formula, right? So see, this is percent S character. S means it is I mean a fractional. This is the fractional value. This is also fractional. This is also fractional. This is also fractional. Percent P character, we can write here capital P, right? So we can use this. I mean, through example, we can justify this with the example. Suppose that if we have methane, so all of you are knowing that in methane, all four hybrid orbitals are equivalent. So what is the angle between two equivalent? See, two or more equivalent hybrid orbitals. So what is the angle between two equivalent hybrid orbitals is here? The I mean what 109 degree 28 minute or 109.5 degree. And what is the percent character? All of you are knowing, we have already discussed that in methane, in every hybrid orbital, so each sp3 hybrid orbital has S is equal to 25%, percent S character is 25, and P is equal to 75, right? P is equal to 75. So if you, I mean, want, you can justify this bond angle. What also we are knowing that 109 degree 28 minute is there, so we can prove that bond angle from this formula, from this relation. So cos theta is equal to, either you can take this relation or this relation. So if I am taking this 0.25, so S is equal to 0.25, because don't put here 25, right? 25%, so you should put the fractional value here, 0.25 by 0.25 minus 1. So after this solution, we will get minus 0.333. So all of you, I will hopefully from maths background, and all of you are knowing that what is the value of theta if cos theta is equal to minus 0.333. So theta is equal to 109.5. So we can, I will prove this with this formula. Means this formula is okay, no problem with this formula. Now, how to apply this formula on the non-equivalent hybrid orbitals like water? You know, in water there is no complete ideal hybrid character in the hybrid orbitals due to the presence of lone pairs, right? So if we consider the water molecule, so now by knowing the angle between, because angle is experimentally we know that what is the angle between two bond pair of electrons. We don't know what is the angle between two non-bonded electrons, but we know that this between bonding electrons in water molecule, that this angle we know experiment. This is 104.5, right? And we don't know exactly what bond angle is there. So by knowing this, because you know this formula, or this formula 2 or more. So if we have knowledge about this value, if we have experimentally, then we can find out that what is the P character here in this. So accordingly, we can find out what is the S character and P character in their lone pairs. One thing is clear, that in all four hybrid orbitals, sp3 hybrid orbitals, P character and S character are not equal. So one thing is always true here, that in all four hybrid orbitals, in water, the S character, S and P character are not equal. Right. Now let's see how to calculate. So if we take this bond angle, so we can write here cos theta is equal to this cos 104.5, and this is equal to, I think, minus 0.25, minus 0.25. So this is equal to, if we can write P minus 1 by P, so this P is equal to, after solving this equation, we get P is equal to 0.8, right? Means 80% P character and 20% S character. Means in these two orbitals through which this hydrogen is overlapped, in these two the P character is 80%, but what ideally should be the P character here? 75%. Means here P character increases. So from where this P character is coming? Obviously this will withdrawn, this P character is withdrawn from this, because there is no other contribution from outside. Everything is here only. You have one S orbital and 3 P orbitals which are mixed. So if here P character increases, so definitely here P character will decrease. So in these two, the P character is 80% and S character is 20%, and here S character originally, ideally this should be 25, but here 20, means here P character is increases, through which this hydrogen overlaps, and S character decreases, right? So if you want, you can apply the simple mathematics, right? Now if we summarize the total, all 4 orbitals in the oxygen must have the P character in Px, Py, Pz, that should be equal to 3. Simple mathematics. So the total P character, summed over all 4 orbitals on oxygen, all 4 orbitals over oxygen must be three. Px plus Py plus Pz, right? And the total S character, is equal to 1. It is okay, because this Px, Py and Pz are involved, and S is total, S is involved here, right? So total S character, this is 1, and total P character, this is 3, right? I'm considering 1 orbital, 1 unit contribution, right? Now see, what is the total P character in the bonding. So we can see if bonding orbitals, means if bonding orbitals they have P character, more P character, then non-bonding orbitals they have less P character, right? So we can say that we have 2 bonding orbitals. they have this 0.8 plus 0.8. These are bonding orbitals. I am talking about these two bonding orbitals. So these two bonding orbitals have 0.8, 0.8. So the non-bonding orbitals must have 0.7 plus 0.7, and this is equal to what? See, this is equal to 3. These two are bonding and these two are non-bonding. Right? And similarly, this is P. And now come to the S. For S, see, in the bonding 20%, so 0.2 plus 0.2 plus. In the non-bonding, how much this S character should be there? 0.3 plus 0.3. So this is equal to what? 1 total S. Because you know, whatsoever character is increasing or decreasing here in this molecule, that must be equal to the original contribution 3 p orbitals and 1 s orbital. Right? Now you can say that in the non-bonding orbitals, so if we can draw here, so this is oxygen. Now this is two bonding orbitals and two non-bonding orbitals, lone pair, right? What is S character here? S character is 20% and P character is 80%. And what is here S character? S character is 30% and P character is 70%. And similar here also. Ideally we are reporting what? sp3, 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 right? So how to represent this hybridization? How to say that in H2O molecule what should be there? S 0.2 and P 0.8, right? So this this percentage here, S and P percentage, I mean here, and here what 0.3 and 0.7. So I mean no need to write like this. So this is the complete picture of this water molecule in the hybrid orbitals. What is the different characters, how much they contribute. So what we can say? We can say that in water molecule, the bonding orbitals have the mixed character between sp3 and pure p atomic orbital, right? So this is called what? Index hybridization, and this is the reason why we can say in cyclopropane, if you remember and see class 11th students, they will find that in this cyclopropane molecule, every carbon is sp3 hybridized, but the bond which is formed by these two, so here this hybridization in this hybridization approximately sp5 hybridization is there. So many people are afraid of, okay, what is this sp, how sp5 hybridization is there. So this is basically not like that. sp5, you know, due to increase in p character, we are saying that okay, this is equivalent to sp5 like that, right? So this type of calculation and concept we will find in other molecules as well. So now, like this water molecule, you can explain ammonia molecule also, and other some other non-equivalent hybrid orbitals, how they have non-equivalent contribution of S and P character, right?